The solid state. We are mostly surrounded by solids and we use them more often than liquids and gases. For different applications, we need solids with widely different properties. These properties depend upon the nature of constituent particles and the binding forces operating between them. Therefore, study of the structure of solids is important. The correlation between structure and properties helps in discovering new solid materials with desired properties like high temperature, superconductors, magnetic materials, biodegradable polymers for packaging, biocompliant solids for surgical implants, etc. From our earlier studies, we know that liquids and gases are called fluids because of their ability to flow. The fluidity in both of these states is due to the fact that the molecules are free to move about. On the contrary, the constituent particles in solids have fixed positions and can only oscillate about their mean positions. This explains that rigidity in solids. In crystalline solids, the constituent particles are arranged in regular patterns. In this unit, we shall discuss different possible arrangements of particles resulting in several types of structures. The correlation between the nature of interactions within the constituent particles and several properties of solids will also be explored. How these properties get modified due to the structural imperfections or by the presence of impurities in minute amounts would also be discussed. In class 11th, you learned that matter can exist in three states, namely solid, liquid, and gas. Under a given set of conditions of temperature and pressure, which of these would be the most stable state of a given substance depends upon the net effect of two opposing factors. Intermolecular forces tend to keep the molecules or atoms or ions closer, whereas thermal energy tends to keep them apart by making them move faster. At sufficiently low temperature, the thermal energy is low, and intermolecular forces bring them so close that they cling to one another and occupy fixed positions. These can still oscillate about their mean positions, and the substance exists in solid state. The following are characteristic properties of the solid state. They have definite mass, volume, and shape. Intermolecular distances are short. Intermolecular forces are strong. Their constituent particles, atoms, molecules, or ions, have fixed positions and can only oscillate about their mean positions. They are incompressible and rigid. Solids can be classified as crystalline or amorphous on the basis of nature of order present in the arrangement of their constituent particles. A crystalline solid usually consists of a large number of small crystals, each of them having a definite characteristic geometrical shape. In a crystal, the arrangement of constituent particles, atoms, molecules, or ions is ordered. It has long-range order, which means that there is a regular pattern of arrangement of particles, which repeats itself periodically over the entire crystal. Sodium chloride and quartz are typical examples of crystalline solids. An amorphous solid, Greek amorphos means no form, consists of particles of irregular shape. The arrangement of constituent particles, atoms, molecules, or ions in such a solid has only short-range order. In such an arrangement, a regular and periodically repeating pattern is observed over short distances only. Such portions are scattered, and in between, the arrangement is disordered. The structure of quartz crystalline and quartz glass amorphous are shown in figure 1.1, A and B respectively. While the two structures are almost identical, yet in the case of amorphous quartz glass there is no long-range order. The structure of amorphous solids is similar to that of liquids. Glass, rubber, and plastics are typical examples of amorphous solids. Due to the differences in the arrangement of the constituent particles, the two types of solids differ in their property. Crystalline solids have a sharp melting point. On the other hand, amorphous solids soften over a range of temperature and can be molded and blown into various shapes. On heating, they become crystalline at some temperature. Some glass objects from ancient civilizations are found to become milky in appearance because of some crystallization. Like liquids, amorphous solids have a tendency to flow, though very slowly. Therefore, sometimes these are called pseudo-solids or supercool liquids. Glass panes fixed to windows or doors of old buildings are invariably found to be slightly thicker at the bottom than at the top. This is because the glass flows down very slowly and makes the bottom portion slightly thicker. Crystalline solids are anisotropic in nature. That is, some of their physical properties like electrical resistance or refractive index show different values when measured along different directions in the same crystals. This arises from different arrangement of particles in different directions. This is illustrated in figure 1.2. Since the arrangement of particles is different along different directions, the value of same physical property is found to be different along each direction. Amorphous solids, on the other hand, are isotropic in nature. It is because there is no long-range order in them and arrangement is irregular along all directions. Therefore, value of any physical property would be same along any direction. These differences are summarized in table 1.1. Amorphous solids are useful materials. Glass, rubber, and plastics find many applications in our daily lives. Amorphous silicon is one of the best photovoltaic material available for conversion of sunlight into electricity. Classification of crystalline solids. In section 1.2, we have learned about amorphous substances and that they have only short-range order. However, most of the solid substances are crystalline in nature. For example, all the metallic elements like iron, copper, and silver, non-metallic elements like sulfur, phosphorus, and iodine, and compounds like sodium chloride, zinc sulfide, and naphthalene from crystalline solids. Crystalline solids can be classified on the basis of nature of intermolecular forces operating in them into four categories, viz. Molecule, ionic, metallic, and covalent solids. Let us now learn about these categories. Molecules are the constituent particles of molecular solids. These are further subdivided into the following categories. Non-polar molecular solids. They comprise of either atoms, for example argon and helium, or the molecules formed by non-polar covalent bonds, for example H2, Cl2, and I2. In these solids, the atoms or molecules are held by weak dispersion forces or London forces, about which you have learned in class 11th. These solids are soft and non-conductors of electricity. They have low melting points and are usually in liquid or gaseous state at room temperature and pressure. Polar molecular solids. The molecules of substances like HCl, SO2, etc. are found by polar covalent bonds. The molecules in such solids are held together by relatively stronger dipole-dipole interactions. These solids are soft and non-conductors of electricity. Their melting points are higher than those of non-polar molecular solids, yet most of these are gases or liquids under room temperature and pressure. Solid SO2 and solid NH3 are some examples of such solids. Hydrogen bonded molecular solids. The molecules of such solids contain polar covalent bonds between H and F, O or N atoms. Strong hydrogen bonding binds molecules of such solid like H2O, ice. They are non-conductors of electricity. Generally, they are volatile liquids or soft solids under room temperature and pressure. Such solids are formed by the three-dimensional arrangements of cations and anions bound by strong Coulombic forces. These solids are hard and brittle in nature. They have high melting and boiling points. Since the ions are not free to move about, they are electrical insulators in the solid state. However, in the molten state or when dissolved in water, the ions become free to move about and they conduct electricity. Metallic solids. Metals are orderly collection of positive ions surrounded by and held together by a sea of free electrons. These electrons are mobile and are evenly spread out throughout the crystal. Each metal atom contributes one or more electrons towards the sea of mobile electrons. These free and mobile electrons are responsible for high electrical and thermal conductivity of metals. When an electric field is applied, these electrons flow through the network of positive ions. Similarly, when heat is applied to one portion of a metal, the thermal energy is uniformly spread throughout by free electrons. Another important characteristic of metals is their luster and color in certain cases. This is also due to the presence of free electrons in them. Metals are highly malleable and ductile. Covalent or network solids. A wide variety of crystalline solids of non-metal result from the formation of covalent bonds between adjacent atoms throughout the crystal. They are also called giant molecules. Covalent bonds are strong and directional in nature. Therefore, atoms are held very strongly at their positions. Such solids are very hard and brittle. They have extremely high melting points and may even decompose before melting. They are insulators and do not conduct electricity. Diamond and silicon carbide are typical examples of such solids. Graphite is soft and a conductor of electricity. Its exceptional properties are due to its typical structure. Carbon atoms are arranged in different layers and each atom is covalently bonded to 3 of its neighboring atoms in the same layer. The fourth valence electron of each atom is present between different layers and is free to move about. These free electrons make graphite a good conductor of electricity. Different layers can slide one over the other. This makes graphite a soft solid and a good solid lubricant. Crystal lattices and unit cells. The main characteristic of crystalline solids is the regular and repeating pattern of constituent particles. If the three-dimensional arrangement of constituent particles in a crystal is represented diagrammatically, in which each particle is depicted as a point, the arrangement is called crystal lattice. Thus, a regular three-dimensional arrangement of points in space is called a crystal lattice. A portion of crystal lattice is shown in figure 1.5. There are only 14 three-dimensional lattices. These are called Bravais lattices, after the French mathematician who first described them. The following are the characteristics of a crystal lattice. Each point in a lattice is called lattice point or lattice site. Each point in a crystal lattice represents one constituent particle, which may be an atom, a molecule, or an ion. Lattice points are joined by straight lines to bring out the geometry of the lattice. Unit cell is the smallest portion of a crystal lattice, which, when repeated in different directions, generates the entire lattice. A unit cell is characterized by its dimensions along the three edges A, B, and C. These edges may or may not be mutually perpendicular. Angles between the edges: alpha between B and C, beta between A and C, and gamma between A and B. Thus, a unit cell is characterized by 6 parameters: A, B, C, alpha, beta, and gamma. These parameters of a typical unit cell are shown in figure 1.6. Primitive and centered unit cells. Unit cells can be broadly divided into 2 categories: primitive and centered unit cells. Primitive unit cells. When constituent particles are present only on the corner position of a unit cell, it is called a primitive unit cell. Centered unit cell. When a unit cell contains one or more constituent particles present at positions other than corners, in addition to those at corners, it is called a centered unit cell. Centered unit cells are 3 types. Body-centered unit cell. Such a unit cell contains one constituent particle, atom, molecule, or ion at its body center besides the one that are at its corners. Face-centered unit cells. Such a unit cell contains one constituent particle present at the center of each face besides the one that are at its corners. End-centered unit cells. In such a unit cell, one constituent particle is present at the center of any 2 opposite faces besides the one present at its corner. In all, there are 7 types of primitive unit cells: cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, triclinic. Number of atoms in a unit cell. We know that any crystal lattice is made up of very large number of unit cells, and every lattice point is occupied by one constituent particle, atom, molecule or ion. Let us now work out what portion of each particle belongs to a particular unit cell. We shall consider three types of cubic unit cells, and for simplicity assume that the constituent particle is an atom. Primitive cubic unit cell. Primitive cubic unit cell has atoms only at its corner. Each atom at a corner is shared between 8 adjacent unit cells as shown in figure 1.8. 4 unit cells in the same layer and 4 unit cells of the upper or lower layer. Therefore, only 1/8 of an atom or molecule or ion that actually belongs to a particular unit cell. In figure 1.9, a primitive cubic unit cell has been depicted in 3 different ways. Each small sphere in figure 1.9a represents only the center of the particle occupying that position and not its actual size. Such structures are called open structures. The arrangement of particles is easier to follow in open structures. Figure 1.9b depicts space-filling representation of the unit cell with actual particle size, and figure 1.9c shows the actual portions of different atoms present in a cubic unit cell. In all, since each cubic unit cell has 8 atoms on its corners, the total number of atoms in one unit cell, 8 into 1 by 8, equals 1 atom. Body-centered cubic unit cell. A body-centered cubic BCC unit cell has an atom at each of its corners and also one atom at its body center. Figure 1.10 depicts A. Open structure, B. Space filling model, and C. The unit cell with portions of atoms actually belonging to it. It can be seen that the atom at the body center wholly belongs to the unit cell in which it is present. Thus, in body-centered cubic BCC unit cell, 8 corners into 1 by 8 per corner atom equals to 8 into 1 by 8 equals to 1 atom. Second, one body-centered atom equals 1 into 1 equals 1 atom. Therefore, total number of atoms per unit cell is 2 atoms. Face-centered cubic unit cell. A face-centered cubic unit cell FCC contains atoms at all the corners and at the center of all the faces of the cube. It can be seen in figure 1.11 that each atom located at the face center is shared between 2 adjacent unit cells and only half of each atom belongs to a unit cell. Figure 1.12 depicts A. Open structure, B. Space filling model, and C. The unit cell with portions of atoms actually belonging to it. Thus, in a face-centered cubic FCC unit cell, 1. 8 corners atoms into 1 by 8 atom per unit cell equals 8 into 1 by 8 gives 1 atom. Second, 6 face-centered atom into 1 by 2 atom per unit cell equals 6 into 1 by 2 gives 3 atoms. Therefore, total number of atoms per unit cell equals 4 atoms. Close packed structures. In solids, the constituent particles are close packed, leaving the minimum vacant space. Let us consider the constituent particles as identical hard spheres and build up 3-dimensional structure in 3 steps. 1. A. Close packing in 1 dimension. There is only one way of arranging spheres in a 1-dimensional close packed structure, that is to arrange them in a row and touching each other. In this arrangement, each sphere is in contact with 2 of its neighbors. The number of nearest neighbors of a particle is called its coordination number. Thus, in 1-dimensional close packed arrangement, the coordination number is 2. B. Close packing in 2 dimensions. 2-dimensional close packed structures can be generated by placing the rows of close packed spheres. This can be done in 2 different ways. 1. The second row may be placed in contact with the first one such that the spheres of the second row are exactly above those of the first row. The spheres of the 2 rows are aligned horizontally as well as vertically. If we call the first row as A-type row, the second row being exactly the same as the first one is also of A-type. Similarly, we may place more rows to obtain AAA type of arrangement as shown in figure 1.14a. In this arrangement, each sphere is in contact with 4 of its neighbors. Thus, the two-dimensional coordination number is 4. Also, if the center of these 4 immediate neighboring spheres are joined, a square is formed. Hence, this packing is called square closed packing in 2 dimensions. Second, the second row may be placed above the first row in a staggered manner such that its spheres fit in the depressions of the first row. And if the arrangement of spheres in the first row is called A-type, the one in the second row is different and may be called B-type. When the third row is placed adjacent to the second in the staggered manner, its spheres are aligned with those of the first layer. Hence, this layer is also of A-type. The spheres of similarly placed fourth row will be aligned with those of the second row B-type. Hence, this arrangement is of AB type. In this arrangement, there is less free space and this packing is more efficient than the square closed packing. Each sphere is in contact with 6 of its neighbors and the two-dimensional coordination number is 6. The centers of these 6 spheres are at the corners of a regular hexagon. Hence, this packing is called two-dimensional hexagonal closed packing. It can be seen in figure 1.14b that in this layer there are some voids, empty spaces. These are triangular in shape. The triangular voids are of 2 different types. In one row, the apex of the triangles are pointing upwards and in the next layer, downwards. C. Closed packing in 3 dimensions. All real structures are 3-dimensional structures. They can be obtained by stacking 2-dimensional layers one above the other. In the last section, we discussed closed packing in 2 dimensions, which can be of 2 types: square closed packed and hexagonal closed packed. Let us see what types of 3-dimensional closed packing can be obtained from these. 1. 3-dimensional closed packing from 2-dimensional square closed packed layers. While packing the second square closed packed layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed over the first layer such that the spheres of the upper layer are exactly above those of the first layer. In this arrangement, spheres of both the layers are perfectly aligned horizontally as well as vertically in shown figure 1.15. Similarly, we may place more layers one above the other. If the arrangement of spheres in the first layer is called A-type, all the layers have the same arrangement. Thus, this lattice has AAA and so on type pattern. The lattice thus generated is the simple cubic lattice and its unit cell is the primitive cubic unit cell. 3-dimensional closed packing from 2-dimensional hexagonal closed packed layers. 3-dimensional closed packed structures can be generated by placing layers one over the other. A. Placing second layer over the first layer. Let us take a 2-dimensional hexagonal closed packed layer A and place a similar layer above it such that the spheres of the second layer are placed in the depressions of the first layer. Since the spheres of the 2 layers are aligned differently, let us call the second layer as B. It can be observed from figure 1.16 that not all triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to different arrangements. Wherever a sphere of the second layer is above the void of the first layer or vice versa, a tetrahedral void is formed. These voids are called tetrahedral voids because the tetrahedron is formed when the centers of these 4 spheres are joined. They have been marked as T in figure 1.16. One such void has been shown separately in figure 1.17. At other places, the triangular voids in the second layer are above the triangular voids in the first layer, and the triangular shapes of these do not overlap. One of them has the apex of the triangle pointing upwards and the other downwards. These voids have been marked as O in figure 1.16. Such voids are surrounded by 6 spheres and are called octahedral voids. One such void has been shown separately in figure 1.17. The number of these 2 types of voids depend upon the number of the closed packed spheres. Let the number of closed packed spheres be n. Then the number of octahedral voids generated is n. The number of tetrahedral voids generated is 2n. B. Placing third layer over the second layer. When third layer is placed over the second, there are two possibilities. Covering tetrahedral voids. Tetrahedral voids of the second layer may be covered by the spheres of the third layer. In this case, the spheres of the third layer are exactly aligned with those of the first layer. Thus, the pattern of spheres is repeated in alternate layers. This pattern is often written as ABAB pattern. This structure is called hexagonal close packed HCP structure, figure 1.18. This sort of arrangement of atoms is found in many metals like magnesium and zinc. 2. Covering octahedral voids. The third layer may be placed above the second layer in a manner such that its spheres cover the octahedral voids. When placed in this manner, the spheres of the third layer are not aligned with those of either the first or the second layer. This arrangement is called C-type. Only when fourth layer is placed, its spheres are aligned with those of the first layer as shown in figure 1.1 and 1.9. This pattern of layers is often written as ABC, ABC and so on. This structure is called a cubic close packed CCP or face-centered cubic FCC structure. Metals such as copper and silver crystallize in this structure. Both of these types of close packing are highly efficient and 74% space in the crystal is filled. In either of them, each sphere is in contact with 12 spheres. Thus, the coordination number is 12 in either of these two structures. Formula of a compound and number of voids filled. Earlier in this section, we have learned that when two particles are close packed, resulting in either CCP or HCP structure, two types of voids are generated. While the number of octahedral voids present in a lattice is equal to the number of close packed particles, the number of tetrahedral voids generated is twice this number. In ionic solids, the bigger ion, usually anions, form the close packed structure, and the smaller ion, usually cations, occupy the voids. If the latter ion is small enough, then tetrahedral voids are occupied. If bigger, then octahedral voids. Not all octahedral or tetrahedral voids are occupied. In a given compound, the fraction of octahedral or tetrahedral voids that are occupied depends upon the chemical formula of the compound, as can be seen from the examples. Example 1.1. A compound is formed by two elements X and Y. Atoms of the element Y as anions make CCP and those of element X as cations occupy all the octahedral voids. What is the formula of the compound? The CCP lattice is formed by the element Y. The number of octahedral voids generated would be equal to the number of atoms of Y present in it. Since all the octahedral voids are occupied by the atom of X, their number would be also equal to that of element Y. Thus, the atoms of elements X and Y are present in equal numbers or 1:1 ratio. Therefore, the formula of the compound is XY. Example 1.2. Atoms of element B form HCP lattice and those of the element A occupy 2/3 of tetrahedral voids. What is the formula of the compound formed by the elements A and B? The number of tetrahedral voids formed is equal to twice the number of atoms of element B, and only 2/3 of these are occupied by the atoms of element A. Hence, the ratio of the number of atoms of A and B is 2 into 2 by 3 is to 1 or 4:3, and the formula of the compound is A4B3. Locating tetrahedral and octahedral voids. We know that close packed structure have both tetrahedral and octahedral voids. Let us take CCP or FCC structure and locate the voids in it. Let us consider a unit cell of CCP or FCC lattice. The unit cell is divided into 8 small cubes. Each small cube has atoms at alternate corners. In all, each small cube has 4 atoms. When joined to each other, they make a regular tetrahedron. Thus, there is 1 tetrahedral void in each small cube and 8 tetrahedral voids in total. Each of the 8 small cubes have 1 void in 1 unit cell of CCP structure. We know that CCP structure has 4 atoms per unit cell. Thus, the number of tetrahedral voids is twice the number of atoms. B. Locating octahedral voids. Let us again consider a unit cell of CCP or FCC lattice. The body center of the cube C is not occupied, but it is surrounded by 6 atoms on face centers. If these face centers are joined, an octahedron is generated. Thus, this unit cell has 1 octahedral void at the body center of the cube. Besides the body center, there is one octahedral void at the center of each of the 12 edges. It is surrounded by 6 atoms, 4 belonging to the same unit cell, 2 on the corners and 2 on the face center, and 2 belonging to 2 adjacent unit cells. Since each edge of the cube is shared between 4 adjacent unit cells, so is the octahedral void located on it. Only 1/4 of each void belongs to a particular unit cell. Thus, in a cubic closed packed structure, octahedral void at the body center of the cube is 1. 12 octahedral voids located at each edge and shared between 4 unit cells, 12 into 1 by 4 equals 3. Therefore, total number of octahedral voids 4. We know that in CCP, each unit cell has 4 atoms. Thus, the number of octahedral voids is equal to this number. Packing efficiency. In whatever way the constituent particles, atoms, molecules, or ions are packed, there is always some free space in the form of voids. Packing efficiency is the percentage of total space filled by the particles. Let us calculate the packing efficiency in different types of structures. Packing efficiency in HCP and CCP structures. Both types of closed packing, HCP and CCP, are equally efficient. Let us calculate the efficiency of packing in a CCP structure. In figure 1.20, let the unit cell edge length be A and face diagonal AC be B. In triangle ABC, AC square equals to B square equals to BC square plus AB square gives A square plus A square equals to 2A square, or B equals to root 2A. If R is the radius of the sphere, we find B equals to 4R equals to root 2A. Or A is equals to 4R upon root 2 equals 2 root 2R. We can also write R equals to A upon 2 root 2. We know that each unit cell in CCP structure has effectively 4 spheres. Total volume of 4 spheres is equals to 4 into 4 by 3 pi r cube, and volume of the cube A cube, or 2 by 2 root 2 r whole cube. Therefore, packing efficiency equals to volume occupied by 4 spheres in the unit cell upon total volume of the unit into 100% equals to 4 into 4 by 3 pi r cube upon 2 root 2 r whole cube into 100, which is equal to 74%. Efficiency of packing in a body-centered cubic structure. From figure 1.21, it is clear that the atom at the center will be in touch with the other 2 atoms diagonally arranged. In triangle EFT, B square equals to A square plus A square equals 2A square. B equals to root 2A. Now in triangle AFT, C square equals to A square plus B square equals A square plus 2A square equals 3A square. C equals to root 3A. The length of the body diagonal C is equals to 4R, where R is the radius of the sphere, as all the 3 spheres along the diagonal touch each other. Therefore, root 3A equals 4R. A equals to 4R upon root 3. Also, we can write R equals root 3 upon 4A. In this type of structure, total number of atoms is 2, and their volume is 2 into 4 by 3 pi r cube. Volume of the cube A cube will be equal to 4 by root 3r whole cube, or A cube equals to 4 by root 3r whole cube. Therefore, packing efficiency equals to volume occupied by 2 spheres in unit cell upon total volume of the unit cell into 100%, which equals to 68%. In a simple cubic lattice, the atoms are located on the corners of the cube. The particles touch each other along the edge, figure 1.22. Thus, the edge length or side of the cube A and the radius of each particle r are related as A equals to 2r. The volume of the cube unit cell A cube equals 2r cube equals to 8r cube. Since a simple cubic unit cell contains only one atom, the volume of the occupied space equals to 4 by 3 pi r cube. Packing efficiency, therefore, is volume of one atom upon volume of cubic unit cell into 100%, which equals 52.4%. Thus, we may conclude that CCP and HCP structures have maximum packing efficiency. Calculations involving unit cell dimensions. From the unit cell dimensions, it is possible to calculate the volume of the unit cell. Knowing the density of the metal, we can calculate the mass of the atoms in the unit cell. The determination of the mass of a single atom gives an accurate method of determination of Avogadro's constant. Suppose edge length of a unit cell of a cubic crystal determined by X-ray diffraction is A, D the density of the solid substance, and m the molar mass. In case of cubic crystal, volume of a unit cell is equal to A cube. Mass of the unit cell equal to number of atoms in unit cell into mass of each atom, which equals to Z into m. Here, Z is the number of atoms present in one unit cell and m is the mass of a single atom. Mass of an atom present in the unit cell equals m into m by Na, where capital M is molar mass. Therefore, density of the unit cell is mass of unit cell upon volume of unit cell equals Zm by A cube, or Z capital M by A cube Na, or D equals to Z capital M upon A cube by Na. Remember, the density of the unit cell is the same as density of the substance. The density of the solid can always be determined by other methods. Out of the 5 parameters D, Z capital M, A and Na, if any 4 are known, we can determine the 5th. Imperfections in solids. Although crystalline solids have short range as well as long range order in the arrangement of their constituent particles, yet crystals are not perfect. Usually a solid consists of an aggregate of large number of small crystals. These small crystals have defects in them. This happens when crystallization process occurs at fast or moderate rate. Single crystals are formed when the process of crystallization occurs at extremely slow rate. Even these crystals are not free of defects. The defects are basically irregularities in the arrangement of constituent particles. Broadly speaking, the defects are of 2 types, namely point defects and line defects. Point defects are the irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance, whereas the line defects are the irregularities or deviations from ideal arrangement in entire row or lattice points. These irregularities are called crystal defects. We shall confine our discussion to point defects only. Types of point defects. Point defects can be classified into 3 types. 1. Stoichiometric defects. 2. Impurity defects. 3. Non-stoichiometric defects. 1a. Stoichiometric defects. These are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defects. Basically, these are of 2 types: vacancy defects and interstitial defects. 1. Vacancy defect. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This results in decrease in density of the substance. This defect can also develop when a substance is heated. 2. Interstitial defect. When some constituent particles, atoms or molecules occupy an interstitial site, the crystal is said to have interstitial defect. This defect increases the density of the substance. Vacancy and interstitial defects are explained above and can be shown by non-ionic solids. Ionic solids must always maintain electrical neutrality. Rather than simple vacancy or interstitial defects, they show these defects as Frenkel and Schottky defects. 3. Frenkel defect. This defect is shown by ionic solids. The smaller ion, usually cation, is dislocated from its normal site to an interstitial site. It creates a vacancy defect at its original site and an interstitial defect at its new location. Frenkel defect is also called dislocation defect. It does not change the density of the solid. Frenkel defect is shown by ionic substance in which there is a large difference in the size of ions. For example, ZnS, AgCl, AgBr and AgI due to the small size of Zn2 plus and Ag2 plus ions. 4. Schottky defect. It is basically a vacancy defect in ionic solids. In order to maintain electrical neutrality, the number of missing cations in an ions are equal. Like simple vacancy defect, Schottky defect also decreases the density of substances. Number of such defects in ionic solids are quite significant. For example, in NaCl, there are approximately 10 raised to power 6 Schottky pairs per centimeter cube at room temperature. In 1 centimeter cube, there are about 10 raised to power 22 ions. Thus, there is 1 Schottky defect per 10 raised to power 16 ions. Schottky defect is shown by ionic substances in which the cation and anion are of almost same size. For example, NaCl, KCl, CSCl, and AgBr. It may be noted that AgBr shows both Frenkel as well as Schottky defects, impurity defects. In molten NaCl containing a little amount of SrCl2 is crystallized, some of the sites of Na plus ions are occupied by Cr2 plus ions. Each Cr2 plus replaces two Na plus ions. It occupies the site of one ion and the other site remains vacant. The cationic vacancies thus produced are equal in number to that of Sr2 plus ions. Another similar example is solid solution of CdCl2 and AgCl. C. Non-stoichiometric defects. The defects discussed so far do not disturb the stoichiometry of the crystalline substance. However, a large number of non-stoichiometric inorganic solids are known which contain the constituent elements in non-stoichiometric ratio due to defects in their crystal structures. These defects are of two types: metal excess defect and metal deficiency defect. 1. Metal excess defect. Metal excess defect due to anionic vacancies. Alkali halides like NaCl and KCl show this type of defect. When crystals of NaCl are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of crystal. The Cl- ions diffuse to the surface of the crystal and combine with Na atoms to give NaCl. This happens by loss of electron by sodium atoms to form Na plus ions. The released electrons diffuse into the crystal and occupy anionic sites. As a result of crystal now has an excess of sodium. The anionic sites occupied by unpaired electrons are called F centers from the German word Farbenzenter for color center. They impart yellow color to the crystals of NaCl. The color results by excitation of these electrons when they absorb energy from the visible light falling on the crystals. Similarly, excess of lithium makes LiCl crystals pink and excess of potassium makes KCl crystals violet or lilac. Metal excess defect due to the presence of extra cations at interstitial sites. Zinc oxide is white in color at room temperature. On heating, it loses oxygen and turns yellow. Now there is excess of zinc in the crystal and its formula becomes Zn1 plus Xo. The excess Zn2 plus ions move to the interstitial sites and the electrons to neighboring interstitial sites. 2. Metal deficiency defect. There are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. A typical example of this type is FeO, which is mostly found with a composition of Fe.0.950. It may actually range from Fe0.930 to Fe0.960. In crystals of FeO, some Fe plus 2 cations are missing and the loss of positive charge is made up by the presence of required number of Fe3 plus ions. Electrical properties. Solids exhibit an amazing range of electrical conductivities, extending over 27 orders of magnitude, ranging from 10 raised to power minus 20 to 10 raised to power 7 ohm raised to power minus 1 meter raised to power minus 1. Solids can be classified into three types on the basis of their conductivities. 1. Conductors. The solids with conductivities ranging between 10 raised to power 4 to 10 raised to power 7 per ohm per meter are called conductors. Metals have conductivities in the order of 10 raised to power 7 per ohm per meter are good conductors. 2. Insulators. These are the solids with very low conductivities ranging between 10 raised to power minus 2 to 10 raised to power minus 10 per ohm per meter. Semiconductors. These are the solids with conductivities in the intermediate range from 0.6 to 0.4 per ohm per meter. Conduction of electricity in metals. A conductor may conduct electricity through movement of electrons or ions. Metallic conductors belong to the former category and electrolytes to the latter. Metals conduct electricity in solid as well as molten state. The conductivity of metals depend upon the number of valence electrons available per atom. The atomic orbitals of metal atoms form molecular orbitals which are so close in energy to each other as to form a band. If this band is partially filled or it overlaps with a higher energy unoccupied conduction band, then electrons can flow easily under an applied electric field and the metal shows conductivity. If the gap between filled valence band and the next higher unoccupied band, conduction band, is large, electrons cannot jump to it, and such a substance has very small conductivity. It behaves as an insulator. Conduction of electricity in semiconductors. In case of semiconductors, the gap between the valence band and the conduction band is small. Therefore, some electrons may jump to the conduction band and show some conductivity. Electrical conductivity of semiconductors increases with rise in temperature, since more electrons can jump to the conduction band. Substances like silicon and germanium show this type of behavior and are called intrinsic semiconductors. The conductivity of these intrinsic semiconductors is too low to be of practical use. Their conductivity is increased by adding an appropriate amount of suitable impurity. This process is called doping. Doping can be done with an impurity which is electron-rich or electron-deficient as compared to the intrinsic semiconductor silicon or germanium. Such impurities introduce electronic defects in them. A. Electron-rich impurities. Silicon and germanium belong to group 14 of the periodic table and have 4 valence electrons each. In their crystals, each atom forms 4 covalent bonds with its neighbors. When doped with a group 15 element like P or As, which contains 5 valence electrons, they occupy some of the lattice sites in silicon or germanium crystal. 4 out of the 5 electrons are used in the formation of 4 covalent bonds with the 4 neighboring silicon atoms. The 5th electron is extra and becomes delocalized. These delocalized electrons increase the conductivity of doped silicon or germanium. Here, the increase in conductivity is due to negatively charged electron. Hence, silicon doped with electron-rich impurity is called N-type semiconductor. B. Electron deficit impurities. Silicon or germanium can also be doped with group 13 element like boron, aluminium or gallium, which contains only 3 valence electrons. The place where the 4th valence electron is missing is called electron hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole, but in doing so it will leave an electron hole at its original position. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of electron that filled it. Under the influence of electric field, electrons would move up towards the positively charged plate through electronic holes, but it would appear as if the electron holes are positively charged and are moving towards negatively charged plate. This type of semiconductors are called p-type semiconductors. Applications of n-type and p-type semiconductors. Various combinations of n-type and p-type semiconductors are used for making electronic components. Diode is a combination of n-type and p-type semiconductors and is used as a rectifier. Transistors are made by sandwiching a layer of one type of semiconductor between 2 layers of the other type of semiconductor. NPN and PNP type of transistors are used to detect or amplify radio or audio signals. The solar cell is an efficient photodiode used for conversion of light energy into electrical energy. Germanium and silicon are group 14 elements and therefore have a characteristic valence of 4 and form 4 bonds as in diamond. A large variety of solid-state materials have been prepared by combination of groups 13 and 15 or 12 and 16 to stimulate average valence of 4 as in germanium or silicon. Typical compounds of group 13 to 15 are INSP, ALP and GaAs. Gallium arsenide semiconductors have very fast response and have revolutionized the design of semiconductor devices. ZNS, CDS, CDSE and HGTE are examples of group 12 to 16 compounds. In these compounds, the bonds are not perfectly covalent and the ionic character depends on electronegativities of the 2 elements. It is interesting to learn that transition metals oxides show marked differences in electrical properties. TiO, CrO2 and ReO3 behave like metals. Rhenium oxide, ReO3, is like metallic copper in its conductivity and appearance. Certain other oxides like VO, VO2, VO3 and TiO3 show metallic or insulating properties depending on temperature. Magnetic properties. Every substance has some magnetic properties associated with it. The origin of these properties lies in the electrons. Each electron in an atom behaves like a tiny magnet. Its magnetic moment originates from two types of motions. One, its orbital motion around nucleus. Two, its spin around its own axis. Electron, being a charged particle and undergoing these motions, can be considered as a small loop of current which possesses a magnetic moment. Thus, each electron has a permanent spin and an orbital magnetic moment associated with it. Magnitude of this magnetic moment is very small and is measured in the unit called Bohr magneton. It is equal to 9.27 into 10 raised to power minus 24 ampere meter square. On the basis of their magnetic properties, substances can be classified into 5 categories: paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. Paramagnetic substances are weakly attracted by a magnetic field. They are magnetized in a magnetic field in the same direction. They lose their magnetism in the absence of magnetic field. Paramagnetism is due to presence of one or more unpaired electron which are attracted by magnetic field. O2, Cu2+, Fe3+, Cr3+ are some examples of such substances. Diamagnetism. Diamagnetic substances are weakly repelled by a magnetic field. H2O, NaCl, C6H6 are some examples of such substances. They are weakly magnetized in magnetic field in opposite direction. Diamagnetism is shown by those substances in which all the electrons are paired and there are no unpaired electrons. Pairing of electrons cancels their magnetic moments and they lose their magnetic character. Ferromagnetism. A few substances like iron, cobalt, nickel, gadolinium, and CrO2 are attracted very strongly by a magnetic field. Such substances are called ferromagnetic substances. Besides strong attractions, these substances can be permanently magnetized. In solid state, the metal ions of ferromagnetic substances are grouped together into small regions called domains. Thus, each domain acts as a tiny magnet. An unmagnetized piece of ferromagnetic substance, like the domains, are randomly oriented and their magnetic moments get cancelled. When the substance is placed in a magnetic field, all the domains get oriented in the direction of the magnetic field, and a strong magnetic effect is produced. This ordering of domains persists even when the magnetic field is removed and the ferromagnetic substance becomes a permanent magnet. Antiferromagnetism. Substances like MnO showing antiferromagnetism have domain structure similar to ferromagnetic substance, but their domains are oppositely oriented and cancel out each other's magnetic moment. Ferrimagnetism. Ferrimagnetism is observed when the magnetic moments of the domains in the substances are aligned in a parallel and anti-parallel directions in unequal numbers. They are weakly attracted by magnetic field as compared to ferromagnetic substances. Fe3O4, magnetite, and ferritides like MgFe2O4 and ZnFe2O4 are examples of such substances. These substances also lose ferrimagnetism on heating and become paramagnetic. Summary. Solids have definite mass, volume, and shape. This is due to the fixed position of their constituent particles, short distances, and strong interactions between them. In amorphous solids, the arrangement of constituent particles have only short-range order and consequently they behave like supercooled liquids, do not have sharp melting points and are isotropic in nature. In crystalline solids, there is long-range order in the arrangement of their constituent particles. They have sharp melting points, are anisotropic in nature, and their particles have characteristic shapes. Properties of crystalline solids depend upon the nature of interactions between their constituent particles. On this basis, they can be divided into 4 categories, namely molecular, ionic, metallic, and covalent solids. They differ widely in their properties. The constituent particles in crystalline solids are arranged in a regular pattern which extends throughout the crystal. This arrangement is often depicted in the form of 3-dimensional array of points which is called crystal lattice. Each lattice point gives the location of one particle in space. In all, 14 different types of lattices are possible which are called Bravais lattices. Each lattice can be generated by repeating its small characteristic portion called unit cell. A unit cell is characterized by its edge lengths and 3 angles between these edges. A unit cell can either be primitive, which have particles only at their corner positions, or centered. The centered unit cell have additional particles at the body center, at the center of each face, or at the center of two opposite faces. There are 7 types of primitive unit cells. Taking centered unit cell also into account, there are 14 types of unit cells in all, which results into 14 Bravais lattices. Close packing of particles results in 2 highly efficient lattices, hexagonal close pack HCP and cubic close pack CCP. The latter is called face-centered cubic lattice. In both of these packings, 74% space is filled. The remaining space is present in the form of 2 types of voids, octahedral voids and tetrahedral voids. Other types of packing are not close packing and have less efficient packing of particles. While in body-centered cubic lattice BCC, 68% space is filled. In simple cubic lattice, only 52.4% space is filled. Solids are not perfect in structure. There are different types of imperfections or defects. Point defects and line defects are common types of defects. Point defects are of 3 types: stoichiometric defects, impurity defects, and non-stoichiometric defects. Vacancy defects and interstitial defects are the 2 basic types of stoichiometric point defects. In ionic solids, these defects are present as Frenkel and Schottky defects. Impurity defects are caused by the presence of an impurity in the crystal. In ionic solids, when the ionic impurity has a different valence than the main compound, some vacancies are created. Non-stoichiometric defects are of metal excess type and metal deficient type. Sometimes calculated amounts of impurities are introduced by doping in semiconductors that change their electrical properties. Such materials are widely used in electronic industry. Solids show many types of magnetic properties like paramagnetism, diamagnetism, ferromagnetism, antiferromagnetism, and ferrimagnetism. These properties are used in audio, video, and other recording devices. All these properties can be correlated with their electronic configurations or structures.